what we've been doing with volumes, right? We're going to figure out a volume of a prism. And then once it's in a volume in a particular unit, we're then going to convert that into how much that's going to cost us, okay? So volume of a rectangular prism, obviously we know is LWH, right? We've got to kind of infer that a driveway is not going to be a pyramid or anything like that. So it is a prism. So I'm going to take 30 meters times 5 meters times 3 centimeters. Is that going to work? Can I do it that way? I got to change the centimeters, right? Okay, so I'm going to rewrite this as 30 meters times 5 meters times 0.03 meters. Multiply that out, you get 4.5 meters cubed, right? Okay. Now, the reason I put everything in meters, because you could change this to centimeters and this one to centimeters, right? But the reason I went to meters on this one was because what my conversion factor was written in terms of, okay? It's in cubic meters, so I should probably get a volume that's in cubic meters. Does that make sense, everyone? We can do it the other way. We can put everything in centimeters and then address that later, but I think this is a little bit easier first to do it this way. So if that's 4.5 cubic meters is my volume, I'm going to multiply that by my conversion rate, okay? And we need meters cubed down here, right? We need dollars up there. Meters cubed cancel out. There should be a 1 there with meters cubed. And that gives me 175. Multiply that out, and I should get, is it 7? Good, 787.5. Like I was saying, if you're, and I'm going to go through this quickly, but if you're a person that neglected the rate here, and you changed everything into centimeters, you would have gone 3,000 centimeters times 500 centimeters times 3 centimeters, okay? And that's going to give you 3 times 5 times 3 is 45. You got 1, 2, 3, 4, 5 zeros. So 1, 2, 3, 4, 5. You would get that number, right? And that would be centimeters cubed. So in order to multiply by my conversion rate, I need these centimeters to become meters, don't I? So I would do this process of, 1 meter times 1 meter, centimeter times 1 meter, centimeters. Now, what would be the number with these centimeters? It'd be 100, right? 100 centimeters for every meter. How many times am I going to get that 100 to show up here? 3, right? Would it be a little bit more concise to just write one fraction as 100 cubed, 1 cubed, centimeters cubed, meters cubed, instead of all 3 of those? Does that make sense, everybody? That's going to get my centimeters cubed to cancel out. And now I've got things in meters cubed. Now I can multiply by the 175 over 1 meter cubed. Those are going to cancel. And it does end up giving me the same exact 787.5. So if you're not paying attention to the rate, I think the conversion process is a little bit more messy. Okay? Would you agree it's a lot easier to convert 3 centimeters than it was to do all that conversion when you did down in the black? Yeah. So that's always kind of thinking about what the problem is providing and where I want to go with this thing to kind of set my steps that I have to walk through. Remember, as we're in any math problem, we don't want to be robots. Okay, robots don't think, right? Okay, so we don't want to just start going through something with no thought behind it and what that's going to produce and the steps that are going to be involved. Every time that you're doing something, think about the implications of that quantity, okay, and that maybe units, so then maybe your next steps. Number 25 says a brick with dimensions 20 centimeters, 10 centimeters, 5 centimeters weighs 1.2 kilograms. Okay, so right here is a volume, right? Okay. We should be able to find it's a brick, so probably a rectangular prism is our argument here. But it weighs 1.2 kilograms. Right there is a conversion rate for us. Okay. It's a volume per some weight. Does that make sense? Okay. Or some weight per a volume. However you want to write it. But if I find the volume of the brick, it's 20 times 10 times 5, which turns out to be 1,000 cubic centimeters, right? But it weighs 1.2 kilograms. Do you see it? That's a conversion rate. For every 1,000 cubic centimeters that I have, it's going to be 1.2 kilograms, right? So if I have 2,000 cubic centimeters, it's 2.4 kilograms. If I have 3,000, it's going to be 3.6 kilograms, right? So there's my conversion rate. We had to do a little bit of work to develop it, but for now we know for every 1,000 cubic centimeters, we have 1.2 kilograms of weight. Okay? Is that all right with everybody? And that's kind of, a common thing, okay? When somebody manufactures bricks, okay, they're going to set up, one brick, one standard is a lot of times what we call it, and then everything else is based off that. All other weights that we determine based off of objects that we're making out of that same kind of material. We don't go and weigh every one of them, okay? We know how much material and as a volume that is in them, and we multiply by the weight or the standard that we've already set up. Does that make sense to everybody? Okay. If we go through and try to look at the second brick is obviously a little bit different. It's 25. Okay, so brick number 2. Okay, we've got 25 centimeters times 15 centimeters times 4 centimeters. Okay, when I find that volume, 25 times 15 times 4, that ends up being 1,500 cubic centimeters. Is that right? Okay, so that's the new brick that we're making. Can I multiply that by our conversion rate right here and see that I'm going to multiply it by its reciprocal so I get my units to cancel out. Okay, so with this cubic centimeters, that cubic centimeters go back. And I multiply that out, I get 1.8 kilograms. Okay. That's a process that goes on a lot in like construction and building, stuff like that. I was talking in the last class. Would you guys kind of make the argument that not every building is this way, but this building is made up of basically, 2 or 3 different types of bricks. Okay. We would like to know how much this building weighs. Okay. Engineers would want to know how much this building weighs. Okay. Because knowing, and they would want to know how much it's going to weigh before they construct it. Because the soil has to be strong enough to support it, right? The foundation that we create has to be strong enough to support it. That's why the old elementary is no longer there, right? The soil wasn't strong enough to support it. It started to sink. I taught at USV for 2 years in McGuffey. They had a brand new school, about 6 years old when I got there. And if you know anything about that area, Black Swamp area, soil is very, very, very rich in nutrients, but it's also not very stable. Okay, it's not a whole lot of clay in their soil. They built that school 6, 7 years later. There's a giant crack down the middle of it because the soil wasn't strong enough to support the weight of that building. Does that make sense? So when they test soil and do this kind of thing, they want to know the weight of the structure they're putting on top of it. Are they going to get a giant scale and weigh the building? Or are they going to say, okay, this is how much one brick weighs, this is how many bricks are going to be in this building, and this is how much of this material or volume of this material, this concrete that we're going to use, convert to a weight thing. Does that make sense? Okay, so this is a process that is pretty useful. The you asked a question about conversions, or sorry, proportions. So you're saying if I have 1,000 cubic centimeters, weighs 1.2 kilograms, can I set up a proportion that says 1,500 cubic centimeters is equal to blank kilograms? Okay, so let's see if this works. If I multiply, you would get 1,000 x equals 1.2 times 1,500, right? And then what would you do to solve for x? Okay, so you have 1.2 times 1,500 divided by 1,000, right? Can I rewrite that, because it's a common denominator now? Or not common, it's multiplication, sorry. It's multiplication. Can I rewrite that 1.2 times 1,500 as 1.2, 1.2 over 1,000 times 1,500 over 1? Is that still the same thing as that? Does that make sense? Okay. So, is 1.2 over 1,000 that right there? It's 1,500, that right there. So when you set up a proportion and you go through all that work to solve for x, are you doing the exact same thing that we did? You are. Okay. My thought is, my argument, I don't want to go through this algebra every time. Okay. I would rather just line things up, multiply straight across top, multiply straight across the bottom, divide. Okay. But yes, that absolutely does work if you set up that proportion if you want to. Okay. This bottom, I want to do the bottom question first here on that second page. Same concept. Okay. We've got a brick here that is made to be 24 by 12 by 4.5, right? Sorry, 15. 15. Okay. So this information right here is providing us our prism. When we multiply that stuff out, you get 4,320 cubic centimeters. Okay. It says it weighs 4.5 kilograms. So for every 4,320 cubic centimeters, we will have 4.5 kilograms. There's our conversion factor. Okay. On the second part, similar to the last question, but instead of making a second brick, we're now making that is a prism, we're making a second brick that is a cylinder, right? So the volume of a cylinder is pi r squared h, right? Okay. So pi says has a diameter of 0.5 meters. Okay. So the radius would be what? 0.25 meters. Now here I'm just going to do some foreshadowing. If I do everything in meters and then want to use this conversion rate, would things work out real nice? No, so I should do everything in centimeters, right? So how many centimeters is 0.25 meters? Careful, if I've got a quarter of a meter stick, how many centimeters is that? It's going to be 25 centimeters. Centimeters are smaller than meters, right? So 25 centimeters. We'll square that and then we'll multiply it by 22. When I square it, okay, so this is centimeters as a unit, this is centimeters as a unit. When I square it, I get 625 times pi. That would be centimeters squared, because I square those units, times 22. Okay. That all equates out to give me 43196.89 cubic centimeters. Is that okay? All right. If you didn't convert the 0.25 to 25, you just have your decimal place in a different spot. So it's the same 4 number, same 3 number, the 1 number, 9689. Just the decimals all messed up. Okay. I'm then going to multiply this by, hey, what unit should go on the bottom here? Centimeters cubed. What should go on top? Kilograms, right? Once I set that up, it tells us how these numbers should be positioned, right? I'm going to multiply by 4.5 kilograms, and then we're going to divide by 4,320 cubic centimeters. Okay? When we do that, this thing weighs 44.99 kilograms. Okay. Seeing some heads shaking up and down, so that's awesome. That's telling me you're doing things right and you understand this concept. A lot of people will get these conversion rates, whether they have to develop them or they're provided for them, and not know, do I multiply by that or do I multiply by its reciprocal? Okay? Setting up the units first will tell you whether you multiply directly by that or you multiply by its reciprocal. We ended up multiplying by its reciprocal, right? Okay? Which is the same concept. Some people ask, well, do I multiply or do I divide? Well, multiplying by that reciprocal is the same thing as dividing by that, isn't it? If we understand that algebra. I like those 3 questions. Okay. There were 4. So we're going to do this one here about the iron. Okay. The whole manufacturing process, obviously there are very, very, very few manufacturing processes anymore that everything is manufactured on site. Okay. From start to finish. So a lot of times, we'll bring in resources. Okay. Bring in blank slabs to melt down and then create into whatever we don't usually at our facility. Maybe we're doing this building rebar. We don't at our facility have a mine that we mine the iron out, and we have a foundry that takes that iron, that ore, turns it into iron, and all that kind of stuff. Okay, that's probably shipped to me from somewhere, right? Well, if I'm a manufacturer of those things, I want to make sure that I can ship it economically again. So probably the best way of doing that is to take the iron ore and smelt it down to iron slabs, because when I ship it, then it's just kind of easier to deal with. So that's what's happening here. Okay, we have these iron slabs that are 15 by 10 by 10. Okay, we're going to take those iron slabs and we're going to melt them down, and we're going to recast them as cylindrical rods called rebar. You guys know what rebar is? Okay, some head shaking yes, some head shaking no. This is rebar. You've seen that at like Lowe's or Menards, or somebody's pouring concrete in a driveway. Okay, so that's the armature or the skeleton of your concrete that gives your concrete a little bit of flexibility so it doesn't crack, right? And it provides strength as well. They're just cylinders, aren't they? Or roughly cylinders? Okay. Now, just kind of a side note, does anybody know why they have these little ridges on them? Huh? Okay, so we don't really want those touching the ground, because then they'll get moisture on them and they'll rust and then break. Do we know why something like that would have kinda, okay? Those ridges, if it was smooth, think about this. Visualize one of those rods smooth. And then think about one that is rough. Which one has more surface area? Yeah, the one with the ridges, the rough one, right? You got bumps on it, so that's more surface area, right? Why would I want more surface area? It's so the concrete, the wet concrete, has something to grab onto, right? Okay, it's got more surface area to latch onto. And then once that concrete dries, I can't pull that rebar out, right? Because it's got, the concrete's got so much more surface area to grab onto it. If they were smooth cylinders and the concrete dries around that, you would likely be able to, with some effort, pull those rebars out, okay? Or they'd slide around. Does that make sense? When things flex and move, it'd be a problem. So, a surface area kind of application, right? We're going to melt those down and create those cylinders, basically. Okay, so when we do this problem, we're going to neglect the ridges. So the volume of one slab would be 15 times 10 times 10, right? 1,500 cubic centimeters. As we read through the problem, it says we're going to cast these cylindrical rods, but it's going to take 4 slabs to make 1 rod, right? So this volume is going to be multiplied by 4. And I'm going to use 6,000 cubic centimeters to make one of these rebar rods, okay, rebar cylinders, okay? So I'm going to take these slabs and I'll melt them down to a liquid. When I melt a solid down to a liquid, does matter disappear? No, okay? So the volume is just in a different state, right? Okay, so the volume is still the volume. It's still 6,000 cubic centimeters, whether it's a solid state or a liquid state. Does that make sense? Okay. So I melt these down, and I'm going to recast them into a cylinder. So the volume for one cylinder, the volume for my cylinder is going to be 6,000 cubic centimeters. Does that make sense? And the volume for a cylinder is pi r squared h. The question at hand is, what is the radius of the rebar rod? What is that r? Okay. Well, do I know that value right now for my rebar rod? It's got to be that, doesn't it? Okay. It's the amount of volume that I have as a melted liquid right now. Okay. So that's 6,000. I'm going to put my units here as well, just so we pay attention to something here in a moment. Pi is pi. R squared, R is what I'm looking for. But H now is 0.75 meters, right? Can I leave it as 0.75 meters? No, okay, because this is in centimeters, right? I'm going to do a little bit of algebra here in a moment. I don't want to divide centimeters by meters. I want to write this 0.75 meters as 75 centimeters, right? If I do my work, this is all multiplication, right? That's a number, that's a number. So can I divide both sides by 75 pi centimeters? So that goes away. Pi's go away. Come over here, divide by 75 pi centimeters. Okay. So that would leave me with 6,000 divided by 75 pi. My units would be now centimeters squared, right? Which is nice, because now I have r squared, right? On the right-hand side. I take the square root of that. If I take square root of centimeters squared, what are you left with? Just a unit of centimeters, right? Okay. So hopefully all that work with the units kind of opens your eyes to the fact that I started with something cubic, I've gone through my algebra, and it gets down to a linear distance, a linear measurement, which should kind of validate the idea of trying to find the radius. We know a radius is just a segment length, right? So it should have a power of 1 with the unit. You multiply that all out, you get 5.0, is it 5 again? 5.046, okay? And it's going to be centimeters for the first time. Okay? One thing that I think some of us struggle with a lot, okay, is that when I have 3 variables, I know 2 of them, I can always solve for the third one. Even if that third one, okay, I guess maybe I shouldn't circle that one. Even if, I'm using a formula where this b is isolated, right? That is still a variable, and that 6,000 can be replaced there. Does that make sense? Okay. A lot of people, I don't know what the reasoning for this is or what the mindset is, but a lot of people will view that capital B as not a variable, and they view it more as a label or something like that. You can replace that with something that you know. In this case, we know it to be 6,000. That make sense? All right. I want to talk a little bit about circles today, or not circles, spheres today. So let's